I'm pleased to invite Sabrina Volponi. Sabrina is a third-year PhD student in Civil and Environmental Engineering and Earth Sciences program within the College of Engineering. Sabrina's presentation is entitled Chasing Rivers, the Mathematics of Clean Water.
Suppose you looked at reviews for a company and saw that 9 out of the 10 products they sold didn't work. Would you buy from them? Probably not. While this is a terrible standard for managing a business, this is precisely the standard that's used for managing our environment. Specifically, 90% of attempts to clean up contaminated streams and rivers fail. The consequence of this is 1.2 million deaths globally each year due to drinking contaminated water. Our success rate needs to improve. So here's where the issue is. Currently, we clean up contaminated streams by making the traditional assumption that pollutants move solely due to the speed of the water and mixing. Let's see why this doesn't work. If we look in the plot behind me, what you'll find is concentration, or the amount of pollutant on the y-axis, and time on the x. The blue points represent experimental data that I collected from a river in South Bend. Notice, the traditional model, given by the yellow line, fails to match the tail end of the experimental data. These two curves can differ by 10 orders of magnitude, meaning the actual amount of pollutant in our rivers can be 10 billion times greater than the concentration being predicted by our model. With such a mismatch, it's no wonder that 90% of our attempts to clean up our rivers fail. It's incredible this approach works at all. So what is the traditional model missing? Well, as contaminants travel, they'll also spend long periods of time trapped in the rocks at the bottom of the river. If we incorporate this into our modeling, we get the orange line, which does a much better job of matching the experimental data. So great, we've got a model that works. But with that said, it is difficult and expensive to experimentally measure a river's ability to store contaminants. As a result, people continue to use the traditional model, even though we know it fails. That's where I come in. My name is Sabrina Volponi, and I'm a hydrologist focused on relating the river's ability to store contaminants to physical and biological properties that are easy to measure. Through a combination of experiments and mathematical modeling, I have found that the types of rocks lining the bottom of the stream, be it small grains of sand versus large cobbles, affect how quickly materials flush out of the system. This is because smaller rocks are smoother, allowing for faster water flow, and the spaces between these rocks are smaller, reducing the river's ability to store contaminants. I have also found that the amount of living material on top of and between the rocks can be directly and linearly related to the river's ability to store contaminants. Changing these results into practice, my results make it easier for people to use better models when attempting to clean up contaminated rivers, improving the odds of success. Because every person should have access to safe drinking water, and I aim to make this happen. Thank you.
Terrific job. You cannot mistake your conviction and passion for what you're doing. So I understand that you have a unique hobby, and somehow it involves birds, but I don't know what that is. So can you tell us a little bit about this hobby and what it is?
Yeah, so I do bird taxidermy. So in undergrad, someone even gave a lecture on how to stuff a dead bird. And the person said at the end, does anyone want to do one? I have a spare. And as a joke, I said, yeah, I'll do one. And the head of my department saw this and took it very seriously.
So you've been doing several since?
Yeah, I got paid Virginia minimum wage to do this.
Wow, congratulations. Now we got a go-to person. You got a bird that you want to be preserved. So thank you again so much. Great job.
Thank you.
Excellent. Both in the presentation and the question.